We're in section 6.2, and we're going to finish up with the Fundamental Theorem of Calculus. Here we're going to relate the derivative and the integral using antidifferentiation. The motivation will be the area under the curve. So pause and read problem 1. We're given a velocity function, and we want to find the distance, so the opposite of what we had before. Now let's remember, and we should know this already, that distance equals rate times time. And that's fine if the rate is constant. But if we have an arbitrary velocity function, maybe this is over time, so I'll call that t. And suppose we have some kind of function like this, velocity function from A to B, where the velocity is constantly changing. Then how do we find the total distance traveled? Well, what we could do is we could take arbitrarily many rate times time products. And what I mean by that is right now we'll have to approximate, but for example, we could say that, well, for this period of time, we traveled roughly this velocity over that period of time. And then we traveled roughly this velocity over that period of time. You see what I'm saying, right? There you go. And we could just keep doing this, right? We could keep adding up these distance times time products and get a rough approximation of the total distance traveled. Does that seem familiar? I hope it does.
You pooped an egg. You pooped an egg.
Okay. So it turns out the total distance traveled between times A and B is going to be the integral from A to B of v of t dt, right? If you'd prefer to use x instead, then that's fine. So that's the beginning of our motivation. But on the other hand, we know that velocity is the derivative of the position function, right? We know that s prime of t equals v of t. So I guess that means that looking at this curve in a certain sense, if we had, I guess the way of sort of illustrating this is that if we're finding the area under the curve, and we're trying to find the rate of change of the area under the curve, I guess at this value x, as it gets arbitrarily thin, it winds up being v of x. And really, it's v of x delta x, but it winds up being divided by delta x, so they cancel out. So the upshot of all this is that the instantaneous velocity of this function equals v of x. Okay? So when we take the derivative of this, we just take the x and we plug it in for t and get rid of the integral. And we're done. And so that's part 1 of the Fundamental Theorem of Calculus. If we define big f of x to be the integral from a to x, a is a constant, x is the variable, of f of t dt, and we're assuming that, I guess, a is between, then it turns out this is the case. I'll write that again. Big F prime of x equals little f of x. Okay? Fundamental Theorem, part 2. And this is the really important one. Okay?
Oh my god. Sorry.
This says that the integral from a to b of f of, I'll call this f of t dt.
Sorry.
equals the antiderivative of f
Brennan, oh my God.
with b
Brennan,
plugged in minus the antiderivative with a plugged in.
No.
Equivalently, you could say the integral from a to b of f of x dx equals big F of b minus big F of a. Okay? So, in order to find the area under the curve, all we have to do is antidifferentiate and plug in the endpoints.
Oh my God.
And then find f of b minus f of a. Let's look at a couple of examples here. Okay?
No.
So, how do we find the area under the curve from 0 to 2? Remember we had this problem a couple of classes ago? Well, we know that the antiderivative of x squared is 1/3 x cubed. And then this is the notation that we write. This means plug in 8, then plug in 0. So we get 1/3 2 cubed minus 1/3
Oh my God.
0 cubed. And, sorry kids in the background here, and we wind up getting 8/3 minus 0. And we get 8/3.
Brandon, why are you not going?
Okay? Let's look at one more example.
Brandon, why are you
Right,
not
so hopefully
going?
Next example, right? And by the way, I hope this shows you how I got that so quickly the other day. Okay? One more example. The integral from 1 to 3 of 5x to the 6th minus 4 is going to equal, well, we know the antiderivative of this, right?
So tech crew, when
It's
the
that,
black
right?
curtain
And that
closes,
equals
if
5/7
curtain
times 3 to the 7th minus 4 times
the
3
lift and stretching out
minus,
the
and then in
wall.
parentheses,
Clear?
5/7
Okay, Christy, you're on the
whoops,
top.
times
Curtain.
1 to the 7th minus 4 times 1.
Someone else is on the mid-traveler.
And you could simplify that a little bit if you wanted, but that's the answer. All we do is we antidifferentiate, plug in our endpoints. Okay, now I'll just do 2 quick examples of the Fundamental Theorem Part 1.
Okay, so music, go.
All this is we just, excuse me, is, sorry about that, is we're gonna take the function and plug in x for t. That's it, done.
Oh yeah.
Again, here, here. And you get rid of all of this and that. Okay? Now, in this case, we just need to be a little careful because here we have this integral. Let's put parentheses around this just to be clear. This is not what the Fundamental Theorem says. We need to switch the x and the -5. So what we do is we flip the bounds, but in order to do that, we make it negative. That was from the integral properties. And so g prime of x is going to equal -1 plus x to the 7th, x to the 6th. Done. One more example here. We won't do this example. That's a little too complicated. For this example, all we're going to do is antidifferentiate, plug in the bounds. Pause the video, see if you can do it. We know the antiderivative of each of these terms. And we just plug in our bounds. Not a very nice bounds in that case, right? And then we just make sure to subtract. And there we go. And that's all.